Good morning, colleagues, ladies and gentlemen. My name is Anderson Shum, Vice President Research at City University of Hong Kong. It is my great honor to welcome you all to today's distinguished lecture series, a platform for groundbreaking ideas and intellectual exchange. We are really privileged to host Professor Max Liu, Vice-Chancellor and President of University of Surrey, soon to be University of Wollongong as well, a globally recognized leader in nanomaterials and sustainable energy. Previously, he served many senior administrative positions. He has been serving as the President and Vice-Chancellor of the University of Surrey from 2016 until 2025, where he led significant advances in global research and innovation there. Professor Liu's distinguished career includes pioneering contributions to functional nanomaterials with over 500 publications and numerous accolades, including Fellow of the Australian Academy of Science. His leadership has driven transformative advances in green energy technologies, making him an inspiring figure for our academic community. Professor Liu's expertise in nanomaterials aligns seamlessly with CityUHK's mission to advance interdisciplinary research for a sustainable future. His lecture, Functional Nanomaterials for Green Hydrogen Production and Storage, will explore nanotechnology's transformative potential in addressing global energy challenges. I'm confident that his insights will inspire all of us today. It is my great pleasure to invite Professor Max Liu to the stage. And on behalf of City University of Hong Kong, I'm delighted to present Professor Liu with a portable tea set adorned with the CityUHK logo and a floral emblem symbolizing the elegance of Chinese culture as a token of our deep appreciation. Please, Professor Li. We now invite Professor C.S. Li, Professor Liu, Professor Wang Zheng, Professor Qi Yunyu, Professor Jian Lu, and Professor Wang Xin, Professor Shouhan Jiang as well, to join us on stage for a group photo to mark this very special occasion. We now move to the highlight of today's event. Professor Liu will deliver his lecture on functional nanomaterials for green hydrogen production and storage. Please join me to give Professor Liu a very warm welcome.
Thank you very much, Professor Shum. Thank you, Professor Li. Distinguished colleagues, friends, thank you so much. I'm delighted to be here. Good morning. So, as introduced by Professor Shum, I'm in transition. I'm kind of jobless at the moment. Right? So officially, I'm still the President and Vice-Chancellor of the University of Surrey in the UK, but I'll take up my new role next week at Wollongong. So what I'm going to do in the next 40 minutes or so is going to share some insight about how nanomaterials play a role in terms of the green hydrogen production, and I'll explain why hydrogen has a color, and then storage, which is part of the critical infrastructure for the net zero future of the energy mix. We are truly living in a rapidly changing world and ever become more complex world. The world is confronting unprecedented challenges, and the rapid changes, for example, in technology. We all know global sea level temperature has been rising, mainly due to the anthropogenic, the man-made CO2 emissions in the last 50 years, right? And that's a very urgent challenge because by 2035, this is 10 years from now, we are across the so-called planetary boundary. beyond which there will be very, very challenging to reverse. So we have about 10 years in terms of drastic changes in terms of the climate challenges. Aviation space, as we are now seeing SpaceX, Elon Musk, and many other companies racing to develop the so-called lunar economy to not only return to the moon, but also to build an economy on the moon, critical minerals on the moon, as well as to Mars. So just look at this fast change from the Wright brothers to Neil Armstrong's landing on the moon. It took 66 years, but now we have drones, we have satellites that's covering the whole lower orbital for telecommunication, of course, the race to Mars. In terms of biology, and those of you who are very familiar with this, the Human Genome Project took 13 years, costing about $3 billion. Now, it's about an hour you can get a whole human genome sequenced, and it costs about $150. And I'm not going to mention about the digital revolution, which we are living in, the AI, generative AI. That all started from the 80s. This is a quite short, in our lifetime, we've seen dramatic changes in digital technologies. And social changes and geopolitical changes, even more dramatic and even much faster. And you would say, well, what's the impact of that? The impact of social changes, as well as geopolitical changes, will impact on national policy and the international relations, which will determine the mega trends of our society, which then again determine the market and the needs of society. So I will close my talk by coming back to this point, how we as scientists and engineers to think about holistically the megatrends, the impact, how we actually going to focus on solutions. Of course, we are not interested in playing the politics, but we should be cognizant of the politics. The late Rick Smalley, Professor Smalley from Rice University, who discovered the buckyball, gave a hearing in the Congress some years ago. This is about 20 years ago. He outlined the top 10 challenges for the world in the 21st century. And this is the top 10 on the list. You can see the denominator is the population, which is also becoming in itself is a problem because the population becomes aging. But population underpins democracy, and education is a key, or lack of education is going to be a bigger problem, and diseases and terrorism and war and poverty. But the top of the tree of the challenges is energy and climate, which is, in terms of the scales, the biggest problem. And that goes without saying that we need to look at the low carbon economy or net zero economy. Of course, many now the COPs now is 2029, then be 30 in Brazil, has set a 2050 goal for net zero. Most of the countries, and China has set a net zero target of 2060. But that's not easy. How we will get there? The net zero concept is all about decarbonizing the economy in terms of our energy mix. So if you look at this chart, it's quite interesting. Wood, of course, has very little hydrogen, but mostly carbon, then coal, oil, gas, and the hydrogen. Hydrogen itself is not an energy source. It's a carrier, it's a vector of energy. So you can produce hydrogen from all these renewable sources, as well as the non-renewable, which is fossil fuel. And hydrogen can be used in aviation, shipping, and road transportation, and many other industrial as well as household applications. So this is the economy that we are driving towards. I mean, it's not the only solution, to the clean energy future, but will be a critical part of the picture in the energy mix in 2050 and beyond. Currently, the hydrogen industry, as an overview, is quite small. It's about 100 million tons hydrogen produced per year, and predominantly used in the chemical production, ammonia and fertilizers, of course, we're familiar with, but now hydrogen gradually is used in backup power, fuel cell driven, some niche applications. Of course, the massive rollout of hydrogen fuel cell cars is not here yet, even though now the manufacturers start to produce more for demonstration, but it's still quite some years away, maybe 10 years away, because the electric vehicles become more popular. But there are lots of problems with electric vehicles in terms of critical minerals and the recycling, and this is something that we should look at in a holistic way. So the hydrogen production, as I mentioned, can be from the traditional resources like fossil fuels, through steam reforming or cracking, you produce hydrogen, or electrolysis from renewable energy. And then you can store the hydrogen in ammonia, in methanol, and ethanol, and also you can distribute through the existing natural gas pipelines, and then utilization. So that's the supply chain of the hydrogen. In terms of the roadmap, the US DOE so far has been very, there's a great foresight, very sort of a visionary in terms of developing roadmap for clean energy and for hydrogen. In this case, was developed about 10 years ago, around 2010. So if you look at this, still very current. We are in the phase 3. The infrastructure investment is ramping up at the moment, expansion of the markets, and in about 10 years' time, so by 2035, is the realization of a hydrogen economy. So that's why I see that, vehicles, shipping, all come on stream. And now, in fact, I'll give you one example, which is something to do with my research in Queensland. So now it's commercially available in terms of the tonnage of hydrogen storage for shipping. Right, the IEA, International Energy Agency, has this perspective published in 2022, which in my view is out of date. It's quite conservative. It projects about 2070, you have significant percentage of the energy mix that will be carried by hydrogen as a vector. The predominant sectors that will use hydrogen most, number one is shipping, and then number two is aviation. So I think for those of you who actually observe aviation, the aviation industry is actually transitioning from the traditional kerosene, the aerofuel, to biomass, and then now gradually start to test piloting hydrogen. There's a cross-Atlantic flight that is powered by hydrogen being trialed at the moment in the UK. And then chemical industries and iron and steel industries, and of course buildings and space heating and so on. So China actually dominating the production as well as the utilization. It's about 29% of the world hydrogen is produced and used in China. Why we assign color? Because hydrogen is colorless, as we know from chemistry. This is a metaphor to describe how hydrogen is produced and how clean is hydrogen. So the byproducts from oil refinery, for example, or any other industry processes is called the brown hydrogen. And when you gasify coal or reforming methane, you produce the hydrogen which is labeled as gray hydrogen because there's a carbon dioxide produced simultaneously. So if you capture carbon dioxide and then sequester carbon dioxide, the hydrogen is labeled as a blue hydrogen. And any hydrogen produced through electrolysis or photocatalysis through renewable energy sources will be the green hydrogen. This is the focus of my talk here. Just to give you a context, a kilogram of hydrogen is enough to drive your car for 200 kilometers, right? And therefore, you need 5 kilograms to drive 1,000 kilometers, which is twice as much of the electrical vehicles today. And 1 kilogram is enough for an American household, which is quite big, to supply the whole household for one day, yeah. So that's the context. The technical economics, I won't give you a lot of details here. The take-home message is that depending on the processes, at the moment, the cost of hydrogen produced from gray hydrogens, the traditional fossil fuel generated hydrogen, is about 2 kilograms. It's commercially viable because that's why chemical industry is using that as a feedstock. However, any renewable energy produced hydrogen is about $5 to $6 US dollars per kilogram. But also depending on the region of the world, you can see China produces the cheapest electrolyzer. So you can see the baseline here. The lower end is the alkaline electrolyzer. And depending on Brazil, produce the cheapest. Depending on the electricity cost of different regions and different technologies. PAM electrolyzers is the top range. Yeah, the bar here. So this is the 2022 figure. I think at the moment, there's a huge competition to develop more advanced electrolyzers because the alkaline-based is limited by the efficiency to about 70% maximum, but normally 62%. So that's why PAM electrolyzers, which is very expensive because the PAM mechanism, you can see this is the PAM electrolyzer, and then the AEM, which is anion exchange membrane-based electrolysis, is the basic electrochemistry. However, there are a lot of factors in terms of lowering the cost of hydrogen production. The two dominant factors are the electrolyzer cost and the electricity. So it's about 80% of those, cost reduction will come from these two elements. The rest is quite small. So therefore, depending on the electricity, where you are, and the whole energy pricing regulation, so you can produce hydrogen between $3 to $5. This is the green hydrogen. The number of new technologies being researched and developed, this is a very busy slide. I don't expect you to read. This is basically characterized as the low temperature range and high temperature. So high temperature based on oxygen ion conductor. It has very high efficiency, theoretically about 100%. But we all know high temperature ceramic materials, you have lots of problems in engineering. The integrity, the kinetics, the stability of the electrode, and then mechanically, if you use on vehicle application, is going to pose a lot of challenges. However, the traditional liquid alkaline-based, is limited by efficiency, right? This is the most matured. Most of the manufacturers in China produce very cheap electrolyzers now, very competitive in the world. In fact, about 70% of the market is Chinese-made. And solid alkaline and this is anion exchange and the proton exchange membranes can go up a bit higher efficiency, but there's various other problems. The design problems, the cost is still very high. But nonetheless, many demonstrations now not mass-produced yet. So they are getting there in the next 5 years, but high-temperature electrolyzers may come on stream in the next 10 years if the engineering problems are resolved. So this is why we look at to the future. I think the photovoltaic electricity generated from renewable to electrolysis, that's a two-step. So you have efficiency loss. In the future, we should look to the sun to directly harvest the energy to hydrogen. So basically convert the photon energy of the sun to hydrogen, and there are many routes to it, in terms of centralized or distributed routes. So the high temperature process, okay, the electrolysis, and then the solar thermal, the photoelectrical, is the longer term. And we're talking about this is the scale of the production. And of course, in terms of distributed, there'll be also microbial biomass conversion, the biomass involved in the electrolysis, in photocatalysis, and so on. So this is something that we've been involved in terms of the artificial photosynthesis, to really look at how we can use chemistry and nanomaterials as the catalyst to convert solar energy to hydrogen. So this chart shows the efficiency in the y-axis and the system complexity in the x-axis. So in terms of the efficiency, of course, this is already high efficiency PV EC, but it's very high engineering complexity, therefore the cost. In terms of the practical solar hydrogen, you need to move towards this, move up to this quadrant. So around 10% solar to hydrogen efficiency will be commercially viable. This is the benchmark. At the moment, most of the photocatalysts, the various people developed, including our own photocatalyst, is about 1 to 2% efficient, direct to hydrogen. You can see that this is something that there's a lot of fundamental research, lots of lab scale demonstration, but larger scale application is still a long way off. So speaking of the photocatalysis, many of you would be familiar, you are expert in this room. So all started from 1972 by Professor Fujishima in University of Tokyo. He published a Nature paper, really elucidate the mechanism of photocatalysis on titanium nanoparticle. So it involves the photon harvesting, so then the electron hole separation, combination, and then you can actually harvest the electrons, okay, scavenge the electrons, or you use the hole as very strong oxidant for redox reaction on the surface. The efficiency is actually the product of three components: the light harvesting, which is determined by the electronic structure, the band gap of the semiconductor, and the charge separation and transfer. It's to do with the surface structure and as well as the crystal structure, and the surface area and the surface active size determine the chemical reaction rate. So we have been working on the engineering of photocatalyst for a long time, and we're trying to optimize the electronic structure. Therefore, on the left-hand side is the absorbance, the redox potential, the carriers, the mobility, and the crystal structure in terms of the bulk diffusion, and surface structure in terms of the reactant and the reactive sites. The key issues really lies in large, we want to enhance light absorption, and preferably the whole spectrum of the sun, not just the UV range. For most of the semiconductors, they are actually very active in the UV range, and better crystallinity, high surface area, a suitable band gap for particular application. Of course, for hydrogen production, there's a special range, and good stability and the cost consideration. So we've been doing this for a long time, and we have developed this understanding of how to optimize the fundamental properties of the nanocatalyst, the photocatalyst, by doping, by heterostructuring, by crystal engineering. So these are the three methodologies who drive towards the center, which is, in doping, it will improve the surface redox sites, and of course the heterostructuring, different type of oxide and metal oxide. Heterostructuring will give you the interfacial atomic structure optimization, and therefore interfacial carrier transfer property will be improved. And of course, the crystalline structure through the crystal size, phase, and shape, and then the surface intrinsic atomic structure can be modified, and therefore you control the surface sites, or the surface state, sorry. So speaking of the crystal engineering, we did some work on one particular photocatalyst. This is many years ago. We used quantum mechanical ab initio calculation to really guide our experiment to search for the method, to realize the highly active facet control that, in amethyst crystal you have 001, and that's shown on the slides, and 101 phase. 101 phase is actually the most stable, and 001 is highly active because it's got unsaturated and oxygen titanium bridges. So we was the first to prove microgrizzle's theory, and this 001 phase can be produced stably, but no one actually been able to do it. So experimentally using hydrothermal and the fluoride doping, we are able to preferentially grow this 001 phase and to have a stable, even after heating, 001 phase to the tune of 47%. Later, in subsequent work, we demonstrated we can go up to 90%. So the photocatalysis is a very complex phenomenon. In order to improve the efficiency, we have to understand, the photocatalysis process happens at different length scale, and this is several magnitude, order of magnitude length scale and time scale. So the photon irradiation and the separation of the electron hole happens very fast, the femtosecond scale. And of course, the transfer or the separation and transfer and then surface reaction at millisecond to second scale. And of course, at nanoparticle level, or from electronic structure level, and then this is atomic structure, and then to the nanoparticle level, and then to reactor level. So if you have biomass involved, of course, biomass can be catalyzed to produce hydrogen, and of course, you have CO2 as a byproduct. It's even more complex because the diffusion of the reactant, the biomass, it takes minutes. So this is something we have to understand, study, and then trying to optimize. Which one you're going to optimize? Of course, by electronic structuring, all these, not doping, the heterostructuring, you can change the band gap, you can change the electronic structure, then you can optimize at the femtosecond level. But also at the reactor level, of course, you have to improve the surface area, of course, the flow, and all that reactor design comes into play. So the key is to reach the solar to hydrogen efficiency about 10%. At the moment, it's very hard to get there. So one of my former students, who is now professor in the Chinese Academy of Sciences, is the director of the Institute of Metals Research in Shenyang. He is very clever because he designed this tandem called so-called artificial leaf for hydrogen to solar, solar to hydrogen conversion. So basically, what it is a perovskite solar cell integrated together with two cold catalysts, iron and nickel oxyhydroxide as the cold catalyst on this bismuth vanadate photoelectrode. And he produced this very high photocurrent, and of course the efficiency is direct solar to hydrogen efficiency for this device is about 6.5%, right? You may say, oh, okay, that's good, like moving towards the 10%. However, it is very complex to make this. This is almost like an integrated circuit, kind of manufacturing. But with the economy of scale, you can produce this. If you can produce this to cross the 10%, maybe 15%, and it's really, really worthwhile because it's getting to the 20%, which is about the solar to hydrogen conversion from the best, solar cell to the best electrolyzer, right? You just times the two efficiencies. Right, let me switch gear to hydrogen storage because you may say, oh, we can produce hydrogen now from the gray hydrogen or blue hydrogen if you can sequester the carbon. What's the big deal, right? But the big deal is the cost. Of course, as I said, $5 to $6. You need to bring that by, quite a large margin to $3 to $2. $2 is ideal. However, once you have economically produced hydrogen, green hydrogen, the bottleneck in terms of the hydrogen economy is still the infrastructure. And storage is key to this infrastructure. This slide, I really like to use this one because it's more than 20 years old. Review article by Alex Zettel. I think he's from ETH. I forgot which institution. Yeah, it must be ETH. So illustrating this passenger car with the various mode of hydrogen stored. This is a compressed tank, right? Of course, technology has moved on. Now we can compress this much further to 700 bar with the composite material, carbon composite material for the cylinder. And this is liquefied hydrogen. This is the lanthanum nickel 5, which is a solid state absorbing this magnesium hydride. So basically, they are in absorbed state. I'll come back to that. It's about 5 to 10% weight percentage. Liquefied hydrogen has a huge problem because a lot of energy loss. Cryogenic liquefaction requires a lot of energy, and the handling will lose a lot of hydrogen. And apart from some niche applications, such as aerospace, sometimes they use liquid hydrogen, and some other niche applications, no one would contemplate this is the future option. So chemical hydride system also suffers weight and cost concerns at the moment, but that's the direction of travel. I will talk about that. This Ragon plot gives you an idea. So that's metal hydride system. This is the specific energy. This is the energy density in terms of volumetric. And of course, diesel, petrol here, very energy dense. Fossil fuels. And of course, this is methanol, the hydrates of light elements. Ammonia is here. And by the way, ammonia, there's a lot of research going on about ammonia as a storage media for hydrogen. But then if you do the whole life cycle analysis, the energy loss is actually tremendous, right? So there's always pros and cons. Now, the US DOE, again, has a target for, this one is a more recent roadmap in terms of the system gravimetric capacity or volumetric capacity by 2020. I think the 2020 target is already met by many materials, and 2025, we're getting closer in terms of the system, volumetric and gravimetric capacity. And now, I think I will show you the next slides. There is a hope that the Chinese, again, is making a breakthrough in terms of commercially produced hydrogen storage materials at very low pressure, 1 atmosphere to 2 atmosphere, which is 2 bar, right? So this chart, this graph illustrates the different state, of course, compressed hydrogen, then liquefied, and this is the various adsorbed or chemical bonded hydrogen state in terms of the various media. So the weight percentage, the IEA has a benchmark 5%, right? And the kinetics has to be favorable in terms of the time required to refill. Charging and discharging has to be within a few minutes, because that's what I think customers now used to. If you drive a hydrogen fuel cell car, you don't want to wait for hours to refill. But at the moment, electric cars, you have to at least wait for half an hour to charge your battery, right? And unless you have a BYD battery now to be released soon, which is 5 minutes. So the real challenge here is the capacity and also kinetics, right? Now, we have been working on this system called light metal hydride system. So this is one of the earlier papers we published, and then we have a patent that was licensed to a local company in Queensland. So this is something we stopped doing after publishing and licensing the technology. For many years, we just forgot about it, and then until last year, there was a big breakthrough on CCTV, China 中央电视台. They reported Shanghai Jiaotong's, the big truck, right? I'll show you the big truck. But by the way, the 5% at that time, this is almost 20 years ago, 2007, it's about 18 years ago. So 5.5% with a catalyst, vanadium, titanium, with a little bit of carbon nanotubes, right? So this actually, through ball milling of magnesium in hydrogen atmosphere, it's very easy to make. But the Professor Ding Wenjiang and also Professor Zhou Jianxin came to see me last year, told me, oh, Max, did you know that he didn't say he copied our methodology, he said, we followed your work, and they also bought the company, Hydroxia company. I think Ziguo may know this company. It's a Unicrest started this company. So they couldn't go anywhere on a mass production. Only the Chinese manufacturers, and then of course the company in, I think it's in Suzhou, that is started by Shanghai Jiaotong, this group. They produced 14.4 tons of magnesium alloy material, and this is the blocks. It's not by ball milling, different method of production, but they do use catalyst, and he couldn't tell me what catalyst they use. Of course, this is secret. And they reach 7.6% weight percentage. And this is the first town-level magnesium-based solid-state materials. You know what? Shanghai Jiaotong is the world best in terms of shipbuilding. So they going to trial this on a tonnage basis. You need tons of this because for this shipping, you need lots of energy. So this is a brilliant, they won the 2024 IEA Hydrogen Technology Program Award. Right, Now, what's the future? So, of course, magnesium hydrate, it belongs to the conventional hydrate, as I said. If you look at this analysis, which is very, very insightful, the different systems, the complex hydride, the adsorbent system, the chemical hydrides, there's pros and cons. If you use the red, yellow, and green flag system to characterize what's favorable for what, for volumetric capacity, gravimetric capacity, reversibility, thermodynamics, which is the energy used, and kinetics, which is the time required, and the charging, discharging, and then the whole efficiency. This is the illustration. I think, the gravimetric capacity will limit the range of the driving range, but everything else is green, right? And of course, with a chemical hydride system, this sodium aluminate hydrate, you have slow kinetics, which for stationary application maybe is okay, but for onboard application, no good. You can't wait for the hydrogen to come out, to drive your car. So these are the pros and cons in terms of how we're going to focus the future research to develop even cheaper and more efficient and high capacity hydrogen storage system. The beauty of this solid materials is that you only require about 2 bar instead of 700 bar, because the customer perception, although it's a perception, when you have a high pressure tank, it's not safe. But in fact, we all know as chemical engineers and chemists, we handle hydrogen, there's no problem, right? It's quite safe because the materials, but the materials is very expensive. The carbon fiber and other alloys, cylinders, is very expensive. So the future, I think Shandong Yao is one of my former postdocs. He's now the dean of the College of Advanced Energy in Sun University in Shenzhen. He produced another review saying that, we should look at this regime. If you look at this, is the temperature range, and this is of course, thermodynamics, the enthalpy of the absorption. So the molecular chemisorption, and this is a new term, involving systems like morph and biometallic complexes, right? It could be the way to make a more breakthrough and lower temperature or room temperature, right? It's almost ambient temperature range. So that is the system that I think, as a pointer, if you are doing research in hydrogen storage, you look at this kind of system and how to mass produce them is quite critical. Let me end my talk by coming back to my point, how geopolitical changes, societal changes, which is moving very fast. We're in the era of Trump disrupting the whole world in terms of trade, in terms of how the policies actually govern the science and research and also industry policies. So that's all going to really affect the needs of the society, the market, and eventually how we can, as a scientist, add value to make the scientific discovery through innovation process to something valuable for our society, right? So there's a lesson in terms of I think Chi Yung's here, I think composite materials people, many in the audience here, are expert. The carbon fiber industry, this is a success story, from approximately 70s, the last century, to about 2020. So this has become a whole commercial development. The way this come about is actually starting from the needs. So, aerospace, of course, is a typical application, and then many other applications now. And then you look at what is the system performance, okay, required. And then you look at what is the materials property requirement. And then, of course, you study the fundamentals of material science to look at, atomic structure and molecular structure, how then you improve the material property, the materials property and then performance at the system level, device level, and then further driving to the market. That's the iteration that the carbon fiber industry has developed. And of course, there's materials, properties of this is structure materials mostly. So in terms of energy production, like the photocatalyst or electrocatalysts for electrolyzers I talked about, as well as the hydrogen storage materials. I've been saying to my students and many students, okay, to study something from, reading paper to identify the knowledge gap is good, and that's how you start. But then once you get into the research, you should look at the whole forest, not just look at a few trees, right? So you can get lost amongst the trees and not seeing the forest. So therefore, just produce something beautiful in terms of the characterization under the microscope, the TEM or high resolution TEM, doesn't mean they will be useful. They're useful in terms of satisfying your scientific curiosity. That's the level. But then you should always go back to the needs. So what is the needs in terms of the system performance and the materials property, and then this is the iteration that will guide you to do more significant research, more relevant research, and eventually more impact research. This is what we should instill into our students and postdocs' minds. That is something will also help your career when you actually start out as a faculty member. You can write a good proposal if you know what's the societal needs, and then from there you can, ask the scientific questions, right? Okay, with that, thank you very much for your attention.
Thanks a lot, Professor Liu, for a very inspiring talk. So now the floor is open for questions. If you have any questions, please raise your hand and you can press the microphone in front of your table. Any questions? Yes, please.
Thank you, Professor Liu. I'm sorry, I'm not a scientist. I'm not an engineer. I'm from the commerce. My company actually is a top 5 clean energy company in the world. So we have been looking for the opportunities how we store our clean energy. But from your talk, I found that quite a lot of research is 8 years or even longer. Does it mean that there's a bottleneck in terms of hydrogen storage research, and how our commerce people can help in this development? Thank you.
Yeah. Very good question. Thank you very much. I think if you look at this slides, right? What I didn't talk about is that in order to make a commercialization success of new material like hydrogen storage materials, just doing this iteration is not enough, right? That's to improve the technical side. I think it's the investment, the evaluation of the whole technology in the context of the commerce and the competition. And all these require the collaboration with people like you, people who actually truly understand market, competition, and the investment payback period and all that. So in terms of your question, how long this type of technology, materials, will be really, massively produced and applied in industry. The Shanghai Jiaotong, the company, I think is Sufan or Sufan. I think the hydroxia is the label I'm familiar with. they produce this 14-ton magnesium hydrate. So they saying in 2 years' time, they'll put on a big shipping, big real ship. So that's the first demonstration in the world in terms of real commercial application. I would say if they pursue this, they have the investors, or maybe you can talk to them. You know, Zhou Jianxin, I have his WeChat, so I can link you. So they probably can roll out to all the big shipping companies. So that would be the first. And the shipping is the #1 sector in terms of the future hydrogen application in 10 years' time. So 5 years, if you can see, a lot of the ship, you know, will use this. That would save the marine environment, and this is huge. It's huge. I forgot the percentage. It's probably 10% of the carbon dioxide, right? So that's my estimate. But I think depending on the material, you know, we can't just rely on one material, which is promising at the moment, which is magnesium hydrate. But there could be new breakthroughs. That's why I said, you know, researchers need to look at new frontiers. Thank you.
Thank you. Yes, please.
Thank you, Max, for the presentation. You have cited about geopolitics and its challenge on scientific research nowadays. I think in the past few years, when you were in Surrey in the UK, you have seen how it has become increasingly difficult for UK to work with China in scientific research, in cultural exchange like Confucius Institute. So now, as you are now moving to Australia, what kind of future of this transnational scientific research do you see between Australia and China?
Well, I think you know, I'm not an expert on politics. You are. This is Professor Zheng, who just came from Lancaster. So, look, I think you know, Trumpism is disrupting the whole world in terms of the old paradigm of international relations. The allied countries no longer trust America, so the credibility of America is actually on a decline, and that's, you know, something we observe. So in a way, you know, strategically, I think this on air recorded. So strategically, it's good for China, right? So because the whole world recognized that, well, the so-called alliance just for the political convenience of the Americans, and now, you know, the new world order has to be built. It will be multipolar, and therefore, you know, the West, let's say Europe and UK, even Australia, now recognize we have to collaborate, continue to trade with China, collaborate with China, you know, Hong Kong, the whole Asia-Pacific region is become ever more important for multilateral relations. So therefore, I see the outlook is more positive than the Biden administration era, and is more positive even than the Trump first administration.
Thank you.
I could be wrong, but you know, maybe you have a better insight.
Yes, please, one more question there.
Yeah, thank you for a very good overall view of the three aspects of hydrogen, which are in the generation, the storage, and also in the use of hydrogen. I'm of the opinion that actually storage of hydrogen should be in its gaseous form in high pressure. But regardless of that, I would like to ask two questions. The first question is, how do you compare hydrogen generated by wind energy versus by solar energy? And the second question is, how do you compare the use of hydrogen in fuel cells versus the use of heat engines?
Right. Okay. There's quite a few questions there. I think in terms of the storage, at the moment, the mature technology is compressed hydrogen, of course. The costs of the systems, if you look at the DOE roadmap, the cost of the system to 2025 system cost is still about, this is twice of the cost at the moment. So normally for 5 kilogram of hydrogen, if you compress it or if you store it in any way you like, has to be less than 1,500, $1,500, that storage system. I think, if you can compare batteries, the best batteries is actually much higher cost than that. But the compressed tank is actually $3,000. So that you need to lower that cost. That's the bottleneck. Even though a lot of buses and trucks, which has the fuel cell engine driving around many cities now, they still use these high pressure tanks. That's the most mature technology. You're absolutely right. But the passenger car is a different story because many people, if you talk, what about show of hands? You want to drive a 700 bar compressed tank in your car or a 2 bar, 1,000 kilometers sort of driving range of hydrogen. Which one you prefer the compressed tank? Yeah, good. And which one prefer the low pressure tank? There's a few more hands, right? Anyway, so it's human psychology. Human psychology, even though I say compressed tank is mature, it's safe, right? But the cost is the key. That's a more commercial development, right? The second one is compared to the hydrogen.
Wind power versus solar.
That one I don't know. To be honest, I don't know much about wind power. Solar, what's the efficiency of wind power? Wind actually has these problems more intermittent than solar, right? So that's probably for a power grid management issue, which is totally outside of my expertise. I think these two are both green hydrogen for sure, but I don't know what's the cost comparison there, to be honest. I think the third element of your question is
use of fuel cell versus heat engine.
Okay. So there's competition. People who work on internal combustion engine. I have a friend who's in Brunel University, Zhao Hua, who is a top expert in this area. They claim the hydrogen combusted in internal combustion engine is actually as efficient as fuel cells. But I haven't seen the real data from the car manufacturers.
That's right.
I think fuel cells, I think still the most efficient. That's based on my knowledge.
Okay.
Any other questions?
Yes, please.
Yes, Zhigo.
Max, as you said, the hydrogen is an energy carrier. Really, it's for mobile energy versus a stationary energy, so you can move it around. And then, do you think ultimately hydrogen will be the energy carrier to move around energy, or there could be some other forms like a liquid, the liquid chemicals, like the petrol sort of thing? We synthesize petrol to fuel the transport.
I know what you mean. I think there are lots of media you can store hydrogen, ammonia, methanol. These are the two predominant ones. But methanol, you eventually have a carbon. You have to handle the carbon, because ammonia is very interesting. So if you catalytically decompose ammonia at modest temperature range, you can then reverse that. Basically, you synthesize ammonia.
You have to go
very
back,
conventional method. But as I said earlier, the holistic energy loss is actually quite tremendous, right? The cost. If you do the so-called cradle-to-grave life cycle analysis, so that is the problem. And of course, people are doing research and developing technology for different applications. For example, if you would want to green the energy used in steel industry or maybe cement industry. So you need the fuel to provide the temperature range. So burning hydrogen may be too high. The flame temperature may be too high, but ammonia will be just right. This is why I think Professor Yibing Cheng from I think Wuhan University of Technology in Shenzhen National Lab, they developed this technology for a particular industry sector. But ammonia wouldn't be suitable for passenger cars. Very difficult. Hydrogen, of course, is much better. So depend on the needs.
Application.
Therefore, my answer is that the future energy mix and the carrier of energy will be also a mixture, not depending on application. Hydrogen will be predominant as a very clean energy vector, but there will be other medium to store energy, including electricity, of course.
Thank you.
So maybe I also ask one question.
Yeah, sure.
Would you agree that hydrogen economy or hydrogen as a way, as a means of energy will be inevitable? And if that's the case, what's the best way for researchers and students now to take advantage of this opportunity to maximize their contribution and impact to this development?
Good, thank you, Anderson. So I kind of alluded to this in my talk. One area is to look at, that busy slides, and I think low temperature to high temperature. If I was a student, nowadays starting to do a PhD, and all depends on the context. If the lab is actually more towards applied research and driving more towards application, so I would choose a thesis topic in the, depending on the needs, goes back to the needs for hydrogen production in terms of green hydrogen production is the solid oxide based, the oxygen conductor based electrolysis to solve the engineering problems so that you can develop a stack to produce hydrogen. And that in that you basically contribute to the engineering, but not much fundamental science already. But if you want to tackle the holy grail of hydrogen production directly from the sun, I would suggest you go into photocatalysis to really, really get down to the mechanistic, understanding the processes happening at from femtosecond to minutes, time scale, as well as the atomic structure to reactor length scale, to do fundamental research, to make a breakthrough, to design the next wonderful photocatalyst, and to improve the property, the efficiency from solar to hydrogen. And in storage materials, I would say the frontier will be to look at, if you do fundamental research, you look at the new material, not metal hydride. Metal hydride, people already done it. We did it fundamentally. Then the engineering people in Shanghai, Jiaotong, and did the mass production. I'm not saying there's no research left, but I think you can make a smaller contribution, to refine it. But to look for new set of materials, I think you have to look at the mechanisms of, the bonding, and then the thermodynamics and kinetics of the process of storage and discharging the hydrogen.
I see. Thank
That's
you,
the
Professor.
3 areas.
Yes, that's very helpful for our students and researchers, I guess. So any other questions from our audience? Yes, maybe the lady first.
For your excellent lecture. And I am a PhD student from Professor Liu Jin's research group. And I have a question that considering the PEM electrolyzer will be constrained by the scarce iridium metal, and the alkaline electrolyzers will have the limitation that the nickel or iron-based materials will have low stability under the high current densities. So which technology pathway do you believe have greatest potential in the next 10 years? Thank you.
Right. Okay, so did you hear that? Very excellent question. I think it's the electrical catalyst used in alkaline base and in the other electrolyzers in PAM or anion exchange. So the PAM and anion exchange we use precious metals, and whereas the alkaline liquid phase is using nickel, and this is the transitional metals. The current technology is very mature. There's not much research to be done. That is the alkaline liquid technology. And I think the Chinese manufacturers competing based on supply of the engineering, the whole design, but the improvement is very, very marginal. It's about 2%, 1% improvement in efficiency to move towards the theoretical 70%, right? And then to lower the cost. So therefore, I think the next 10 years, your questions, which one's more promising? Of course, I would say PAM, AEM, and then the high temperature oxide-based, ceramic-based electrolyzers for the production of hydrogen. And there'll be a lot of scientific and material science and engineering and the whole mechanical engineering of the systems that need to really advance to solve that problems. So it could take more than 10 years for the ceramic type, because I know one of my former students, who's our professor in Queensland, he worked on solid oxide fuel cells, and he's reversed the cycle to produce hydrogen, and he published all the papers and got a few patents, but still, he got the best engineers from BHP who actually lost their job, in terms of the solid oxide fuel cell, how to make the stacks. But after 5 years, he said, I'm giving up because this is too difficult in terms of commercializing the technology. We really require the big companies, like BYD and other companies, and they have so many engineering talent. So why people look to China? Because China has the scale and the capacity, capability, and the talent in terms of engineers. So that's what make a difference, and why the Western countries can't really reestablish the manufacturing base. They could if they take another 50 years, but the whole economy is moved towards service economy. There's no going back. So, I mean, no matter which president in the United States, wanting, no matter how many billions, hundreds of billions investment, it's very difficult to reproduce what China has done in the last 40 years. It's just the whole ecosystem. You have to really take decades and decades, and not just the money, but consistent national policy, which doesn't exist in the West. Right. Thank you.
Thank you. So one last question there.
Thanks for the talk, and perhaps a slightly less informed question, as I'm not from academia. I just want to ask, there's a few mention of hydrogen in passenger cars and buses, but as batteries are both increasing in range and coming down in costs, what's the case for hydrogens versus batteries? Yeah, if you can expand. Thanks.
Good question. I mean, batteries now, of course, keep improving in terms of driving range, in terms of the cost is lowering. However, people tend to forget, when we actually have 20% of the world's fleet actually on electrical, the supply for lithium, let's say lithium is now predominant battery material, is probably enough. When we reach 40%, I think the whole Earth's reserve will be exhausted, the mineable lithium resources. So that's the bottleneck, right? So you want to fully electrify the transportation vehicles on the road across the whole world. Of course, China has very high percentage already. The materials, the critical material supply is an issue. The driving range, even though there's Toyota, I think there's also a Chinese battery manufacturer, I forgot, it's in Fujian, and they actually come up with the solid state battery that can drive more than 1,000 kilometers. But still, compared to hydrogen, hydrogen, if you compress 5 kilograms, already 1,000, right? Trucks, buses, is even better for hydrogen, right? Because battery-powered trucks will not go very far. But if you want to go 1,000 kilometers, long-distance shipping by truck, I think hydrogen is the only solution in the future in terms of the energy density. And people wondered whether methanol has a low energy density, would play a role in vehicles. Methanol-based fuel cell is not efficient, and you have a lot of other problems. But it can burn ethanol, of course, that's what we do now. So in terms of the future mix, there will be, I think in the next 20 or 30 years, of course, a mixture of battery-powered electric vehicles, and there will be more fuel cell cars on the road. However, the energy mix in the future, let's not forget one other important energy mix, energy source, that is nuclear. So nuclear technology is also keep advancing to the extent that modular reactors, the pebble reactors, the fourth generation will come on stream, even though the time frame for nuclear fusion is long, long way, maybe 30 years or 40 years or 50 years. So in the future, I think will be, in the next 50 years, will be a mix of everything. Even fossil fuel will still exist, right? Because we can't switch overnight from fossil fuel to other renewable sources, just not enough, right? And also the infrastructure for fossil fuel is there. It's too expensive for any commercial commercial companies or for any nation to overnight replace the infrastructure.
Thank you. So with that, please join me to thank Professor Liu once again for a very inspiring and thought-provoking talk covering both science, technology, education, policies, etc. I think it gives us a lot of room for thought about what to do in terms of research, future career, and research directions. So thank you once again, Professor Liu. I'd like to thank you all for attending this distinguished lecture. You can continue to interact further after the talk, and I think Professor Liu will be with us for a little bit more, and we hope to continue to interact with Professor Liu, and soon to be also President of the University of Wollongong and the Wollongong community. Thank you.
Thank you. Thank you very much. Thank you very much. Thanks.
And thank you to you all. Have a nice day, and thank you to all our colleagues for making this possible.